In this section, I'm going to talk about emission production, and I'm going to kind of come at it from a mainly automotive point of view. But what I say can also be used, obviously, for other combustion systems, and particularly towards the end of this section where I talk about how the emissions change with air-to-fuel ratio. That's generic across any combustion systems. But as I say, because automotive emissions are quite current at the minute, it's going to mainly have the automotive focus. So I'm first going to sort of talk about the difference between compression and spark ignition engines, because it's important to get this understanding, because by nature of their the way that the engines work, they naturally produce different sorts of emissions depending on as a result of their, as I say, as a result of the way that they work. So before I explain that, just want to remind you really of when you were at school and you used to operate a Bunsen burner, and talk about the difference between diffusion flames and premix flames. So if you remember, when you first turned on your Bunsen burner, you turned on the gas and you got this nice orange flame which was leaping up and flickering and everything. Now this is called a diffusion flame. It's called a diffusion flame because the only thing that you're putting up the burner is fuel. So the only way that this flame can burn is to react with that air in its surroundings. So it diffuses into its surroundings and it burns with that. Okay. The reason this is so orange is because a lot of soot is basically being produced in this flame. When you see orange in a flame, what you're really seeing is the soot that's being produced, and the soot glows a particular wavelength, which is that orangey yellow that you see, and so it's the particulates being soot, and that's characteristic of a diffusion type flame. And in fact, just to kind of illustrate this, if you were to look at a hydrogen diffusion flame, this is a bit confusing what I just said, but because there's no carbon in that can't have this orangey glow. But for all other hydrocarbons, you get this orange glow as a result of the soot. So going back to the Bunsen burner, so there's a little valve at the bottom, if you remember, and as you open that, the flame started to change colour. It went from this yellow flickery one down to this kind of roaring blue flame, if you remember. And what's happening there is, as you open the valve at the bottom of the Bunsen burner, you're inducing air into the burner. So rather than just pure fuel going up the middle, you've now got fuel and air. It's pre-mixed, so the fuel is pre-mixed with the air. And this results in a much cleaner combustion. So you can see you've moved from the sooty orangey diffusion flame into a nice clean blue roaring premix flame. Okay, and this is essentially the difference between compression and spark ignition flames. So in terms of a compression ignition flame, so just remember the fuel is injected when the temperature and pressure of the in the cylinder, when the temperature and pressure is above the auto ignition temperature of the fuel. So the piston comes up, fuel is injected, and the conditions are such that it auto ignites. So because it's not pre-mixed, the fuel is injected kind of into the atmosphere. It's a diffusion flame. Strictly speaking, it isn't a diffusion flame. I should make that clear. But it's a diffusion type flame because you haven't got very much time for mixing, and the fuel is quite concentrated. And this is why diesel engines are quite sooty, because you've got this diffusion type flame pour mixing, so you end up with a soot. By contrast, the spark ignition flame, because it's the ignition of or combustion is controlled by a spark, you have a lot more time for the fuel and air to mix, and the fuel is actually often mixed with the air sometimes before it goes into the cylinder if it's a port fueled injector. So you've got plenty of time for the fuel and air to mix. The spark ignites it, so you have a premix flame, which is more like on the right over here. So it's much cleaner from a particulate point of view. Now there's a really good video that kind of helps illustrate what I've just told you. And I can't obviously put it on here for copyright reasons, but there's a link for you. I suggest you go and look at it, or scan the QR code, that'll take you there as well. It's a BBC Bang Goes the Theory. It's about 3 or 4 minutes long. It's pretty good. Go and look at it. The final thing I wanted to talk about in this little section was how the comparative concentration of the emissions in the exhaust changes with air fuel equivalence ratio. Okay, so this is stoichiometric. We're fuel rich here and fuel lean here. So firstly, let's look at carbon monoxide. So we said, if you remember at the start of this session, that carbon monoxide is formed due to incomplete combustion. So basically when it's fuel rich, oxygen lean. So there's not enough oxygen to go around. So it makes sense that when you're fuel rich, you have a lot of CO2 because there's not enough oxygen to fully combust, to achieve complete combustion. Then as you start increasing the air relative air concentration, the CO drops dramatically, and obviously the leaner you go, they will keep mopping up the rest of the carbon monoxide. But essentially you have very low levels around stoichiometry, and obviously when you go fuel lean. NOx looks completely different. So NOx is almost this parabolic shape, and what you need to remember here is, if you remember when I was talking about how NOx is formed, I said the dominant formation of NOx is thermal NOx, i.e. linked to the temperature. So this variation of concentration of NOx broadly follows the variation of flame temperature with air equivalence ratio. And it does. But maybe some of you remember, if you go back and look at the combustion video, I said that your peak flame temperature was ever so slightly rich. And you might notice that the peak NOx is ever so slightly lean. And the reason for that is if you consider, if you start in a very fuel-rich region over here, and as you move towards stoichiometry, the flame temperature is increasing, so your NOx is increasing, that's fine. But once you start going past this peak, the temperature won't have dropped too much, but you've got slightly excess air for combustion, or slightly excess nitrogen. So that's why this peak occurs at slightly fuel lean conditions, is because there's excess air or excess nitrogen around. The temperature hasn't dropped too much, so you kind of get your peak here. Then obviously as the temperature drops, even though you've got excess nitrogen around, because it's linked to temperature, that also drops. So that's why you get that peak there. The unburned hydrocarbons, I think I mentioned this in the combustion lecture as well, but I'll also talk about it here for completeness. And essentially this is linked to flame temperature as well. So imagine around stoichiometry, that's where you've got your minimum unburnt hydrocarbons and your maximum fuel economy. Then as you go either side of here, the same thing is happening. As you reduce the so you can understand if you're going lean, you'd increase your, as you're going rich, you'd increase your unburnt hydrocarbons because there's not enough air to react with the hydrocarbons to completely combust it. But as you go lean, this is linked to flame temperature because there isn't enough temperature to break down the fuel completely. So your unburnt hydrocarbons also increase as you go fuel lean as well as fuel rich, and it is due to slightly different things.